Welcome back. This is not a lesson in and of itself. This is just a little mini deal looking at the unit circle plus the values of it that we need to know and how to remember them, and some patterns. I know that a lot of people look at the values of the unit circle from the standpoint of special right triangles. Personally, I remember my special right triangles because of the unit circle. To me, the unit circle is a real tangible thing that I can see in front of me as I'm working problems. Hopefully you guys can get to the same point, but I know that everybody thinks of it just a little bit differently. So this is my take on it. First of all, a unit circle is a circle with a radius 1. That is the unit circle part of it. And we look at the radian measurements, which we've seen. We can start at 0. Also, if we go all the way around the circle, we have 2 pi radians because of the whole circumference thing. So if we only go halfway, over here we have pi. If we do half of that, we get pi over 2. So we can have 0, half of pi, 2 halves pi is pi, and then down here is going to be 3 halves pi, or 3 pi over 2. And then from here, so we have the pi over 2, we can cut it in half again and get pi over 4. Well, so we have 0, 1/4 pi, 2/4 is pi over 2. We can go the other way, so we have 3 pi over 4. 4 pi over 4 is pi. 5 pi over 4. 6 pi over 4 reduces to 3 pi over 2. And then 7 pi over 4. Then 8 pi over 4 is just 2 pi. So now going back to the pi over 2, in addition to cutting it in half, we could cut it in thirds. So 1/3 of pi over 2 is going to be pi over 6. And we have 2 pi over 6, which reduces to pi over 3. And 3 pi over 6 is pi over 2. 4 pi over 6 reduces to 2 pi over 3. 5 pi over 6. 6 pi over 6 is just pi. 7 pi over 6. 8 pi over 6 reduces to 4 pi over 3. 8 pi over 6, 9 pi over 6 is 3 pi over 2. 10 pi over 6 reduces to 5 pi over 3. 11 pi over 6, which is a tough one to write because the 11 and the pi. And then 12 pi over 6 is again 2 pi. So these are the angles around the unit circle, and each of these angles starts at the horizontal positive x-axis and goes to the that radius, that line. So it could start and then go all the way over there. So those are the angles. Now we're going to take a look at the values. So here I just copied exactly what we had on the other one and put it right here. And so the values, the x and y, remember that in the unit circle, the x is going to be the cosine of the angle, and the y is going to be the sine of the angle. So we have cosine theta comma sine theta. So let's take a look at what these angles are. We can start out at the cardinal positions, which are just the straight over, straight up. Like over here, we have the point 1, 0. And then up here is 0, 1. Way back here is -1, 0. And down at the bottom is 0, -1. So those ones are the easy ones because they're right on the lines. Now, the other ones, there are ways of remembering them. So I'm going to start out with the sine values, so the y values. We're going to start down here at 0, and then we're going to go up. So we have 0, then we have root 1 over 2, root 2 over 2, root 3 over 2, and then this one is root 4 over 2. So now a couple of these simplify. For instance, the root 4 is just 2 over 2 is 1. And then the other one that simplifies is the square root of 1 is just 1, so this one's really just 1/2. So we don't need the root there. But the pattern though, 0, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. It's just going to continue because this 2 pi over 3 angle, like the y value here, is going to be the same as the pi over 3 angle. So it's going to go back down. So we had root 4 over 2. Now we're going to go back down to root 3 over 2, root 2 over 2, root 1 over 2, which is just 1/2, then 0. Now it's going to go into the negatives, but the numbers are going to be the same. So we have 0, we have root 1 over 2, except negative, negative root 2 over 2, negative root 3 over 2, negative root 4 over 2 is negative 1. And we go back. Negative root 3 over 2, negative root 2 over 2, and negative root 1 over 2, which is just negative 1/2. And then back to 0. And so the signs, notice there's only a couple values here that we actually have to know. The cosine is the same thing. The pattern just starts at a different place. It starts at 1, and then it's going to go down. So we have 1, which is root 4 over 2. Then we go to root 3 over 2, root 2 over 2, root 1 over 2, 0. Now we're into the negatives. Negative root 1 over 2, so negative 1/2. Negative root 2 over 2, negative root 3 over 2, negative 1. And then, continuing with our pattern, we have negative root 3 over 2, negative root 2 over 2, negative root 1 over 2, 0. Back into positives, root 1 over 2, root 2 over 2, root 3 over 2, and then back to root 4 over 2, which is 1. So the sines and the cosines are always they're always just these couple values for these values on the unit circle. Now we could have any angle we want, and it's not necessarily going to come up here, but these are the special ones that we actually know and learn. And being able to go back and forth when we have inverse trig, if we have the inverse sine of root 3 over 2, we look to see, all right, so where is it root 3 over 2? The sine, the y value, which is pi over 3 and 2 pi over 3. So that would be what we could get there. Ways of learning these. So first of all, these things come in pairs. 0 and 1 are always together. Root 2 and root 2, or root 2 over 2 and root 2 over 2 are always together. Root 3 over 2 and 1/2 are always together. Sometimes it's root 3 over 2 comma 1/2, sometimes it's 1/2 comma root 3 over 2. And then any of them could be positive or negative. So what can we look at for the patterns? First of all, let's draw a rectangle. Well, the cardinal direction, 0 and 1s, are just 0 and 1s. But let's draw a rectangle through these pi over 6s. So we're talking about the reduced ones, because sometimes they reduce to pi over 3s. But the pi over 6s, things to notice about these. Let's do orange. So we have the pi over 6s. Notice they're all root 3 over 2, comma 1/2. Notice this makes a rectangle that's kind of like short and fat. These are the ones that are right next to the x-axis, are all the pi over 6s. And that would be pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. So all the pi over 6s give us a root 3 over 2, comma 1/2. It might be positive or negative for each of those pieces depending on which pi over 6 we have, but those are going to be the numbers. We can draw a square through those blue ones, the pi over 4s. What do we notice about all these? First of all, they're all pi over 4s. The pi over 4s are going to be the 45-degree angles. So we have the pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Notice those numerators are all odd multiples of pi because the even ones reduce to pi over 2s or to pi itself. So all the pi over 4s, if we look at their points, the coordinates, are both the root 2 over 2 comma root 2 over 2. Now they might be positive or negative depending on which quadrant we're in, but they are all just root 2 over 2 comma root 2 over 2. And finally, let's look at those pi over 3s. Now this one makes that tall, skinny rectangle. These are the ones closest to the y-axis. But they're all pi over 3s. Notice pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. All the other angles that would have been over 3 reduced. So all the pi over 3s, notice those are going to be the 1/2 comma root 3 over 2s. So if you have an angle, let's say it's 37 pi over 3. Well, the 37 over 3 is already reduced, so we know it's going to be something pi over 3. It's going to be 1/2 comma root 3 over 2. Now, it might be positive or negative. We have to figure out what quadrant we're in, but it's going to be that pair, that 1/2 comma root 3 over 2 is going to be the same. So if I have an inverse cosine of root 3 over 2, I know that that's going to be a pi over 6 because the pi over 6s are where the cosine value gives us that root 3 over 2. So seeing these patterns is useful, and I love the little diagram, like once we get all the squares and rectangles on there, because looking at this unit circle as it is now, I feel like I'm making a trench run on the Death Star, and so that just adds to the whole joy of the unit circle. But this is what we're doing. So we do it with the trig, where we plug in the angle and we get those values out, and we do it with the inverse trig, where we plug in the values and we get the angles. Now the inverse trig will give us one of the angles, but not both. We have to look for the other one. Where else is that value the same? Because most of these values happen twice on the unit circle for each x and y. We can go around the circle multiple times by adding a 2 and pi. That would be like if we have pi over 6 plus another 2 pi would give us 13 pi over 6, plus another 2 pi would give us 25 pi over 6, because every time we go around the circle we get it. So that's the general case. A lot of times we won't be looking for every single possible value because there's an infinite number, because it keeps hitting it. Usually we're just looking for once or maybe twice around the circle, at least when we get into the application type problems. So I hope this helps. Attached to this, I have a PDF file. I recommend printing it out and filling it out. One side of it, or it's 2 pages. When I make copies, it's 2-sided. One of the pages is a unit circle, where you basically just fill it out as this. The other side, you have the angles, so you convert the angles from radians to degrees, or vice versa, so you have both of those angles on there, and then all 6 of the trig functions. Really, you only need to do about 4 of them until all the numbers and all the calculations are going to repeat themselves. So it looks like a lot of work, but it's not. But by doing it the way it's set up, there's more patterns that you can find in those trig functions to help you out. And then if you have that sheet, that'll help you with going back and forth as you're working problems as well, until you get them more memorized. So I strongly recommend that. It is not an assignment, but it will help you. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.